Thank you very much. I'm sorry I'm not Benton Clark. He gives great talks. He's a big thinker and has a lot to say. He's been involved in the Mars exploration program since the Viking mission, so it's a little sad that he's not here. So what you're looking at is ATP synthase. It's a huge molecule, equivalent mass of 50,000 carbon atoms. It sits in the wall of cells, and it takes protons, which are concentrated at the bottom in this picture. They rotate the stem, and they changes the conformation of the top, and it takes the ATP, ADP and phosphate are in this more dilute solution. They get captured by the rotating molecule, and it produces an ATP. ADP to ATP. This molecule is, or something very close to it, is present in virtually every living thing. That's how how everything produces the energy molecule, adenosine triphosphate, that is used in many reactions. So it's a really fundamental molecule. So the next picture is flipped, unfortunately. So the rotating part is on the bottom now. The concentration of protons is at the top. And the reason I put this up here is that this ATP synthase is a huge molecule, and it's required by everything. And it uses the flow of protons, this time from the top to the bottom, to make the ATP. What was missing in the first picture is how that proton concentration happens. And all living things today have a set of molecules that in the cell wall, these, that create that flux of protons. And so you might ask, well, which came first? This complex that produces the ATP, or the sequence of other molecules that produce the gradient? And people who have thought about this long before me said, well, I think you've got to have this first to make the ATP. And so something else, and this had to come second. So something else had to produce this concentration of protons in the environment. So I just want to say when ATP appeared, so it's shared by everything up here, and so that there are things that are not shared up here, like the type of cell wall is different between these. So something happened here. ATP synthase, the genetic code, other things happened over 3 billion years ago. And our last common ancestor is in this region too. So our last common ancestor, universal common ancestor, also had ATP synthase. So the people have been thinking about what came first, the ATP synthase or the system that produces the proton gradient. Started thinking about this, and recently some colleagues of mine and I started thinking about it as well. The common thinking is that here on the Mid-Atlantic Ridge, you get a natural gradient of protons by the mixing of hydrothermal waters. And it's widely cited, widely talked about mechanism. So my colleagues and I have been talking about another mechanism, which I want to spend a little more time on here in a Mid-Ocean Ridge system. So this is the model of Russell Martin, Nick Lane, in which here is the Lost City chimneys. These are massive, tens of meters high. They're made out of carbonate, and they funnel high pH water from the seafloor, from the bottom, in the crust, up through these chimneys, out into seawater. And so the seawater pH there is about 7.5. This is 10. So right where this mixing occurs, here, this is a little section of a carbonate chimney, and this is only about 3 centimeters across. the high pH fluid is coming through here and mixing in this region right at the edge of the chimney. So you got 2.5 units of pH difference right here. So lots of protons here, not many protons here. If you had a little chamber in this region, you could produce a proton flux, a natural proton flux, which is what people are looking for. So this is their model. So here's the chimney. Here's a proto cell, a self-assembling membrane, and here's the low pH high proton concentration on the outside. Here's the vent water down here, pH 10, and this protocell sits between. And if you were to put some sort of proto mechanism for converting the proton flux into an energy molecule, it would sit in this cell wall, or this protocell wall. That's the model for hydrothermal chimneys. So the one that we came up with was uses a system which is vast in the oceans. This ocean crust aquifer covers about 60% of the Earth's surface in the sea. Here's some details. This one on the Juan de Fuca Ridge is 64 degrees. There's no oxygen. pH 7.5, which is not too different from seawater. It also has some traces of compounds that are important for life. And in there, we think the natural proton gradient is formed. So I didn't bring up this big chunk of basalt, which I brought with me. On the seafloor, there are these really heavy, dark, black rocks, which for now, almost 20 years now, we've been talking about these little tunnels that form inside the rock. So this big chunk of rock has cracks through it, and starting at the cracks, there are tunnels that extend out into the glass. So this is solid material. This is an open fracture, which would have water in it, and these tunnels have formed somehow. I wouldn't say the consensus. A lot of people think they're biological. They may not be, but I think they are. So the question that we were approaching was, how do these things form? And what is going on in this dark region that we can't really see very well? So, back up just a second. So if you cut one of these tunnels in half or across there and look at it in detail, it looks like this. So this is the solid rock, solid volcanic rock glass. This is the interior of the tunnel, and this is all fibrous, porous phyllosilicate, clay. And this barrier here somehow forms along that tunnel. And whoops, I see what I did something wrong here. So the alteration of volcanic glass to clay happens by the replacement of all the cations in the glass by protons. So all of this used to have a lot of elements in it that are now gone. A lot of calcium, magnesium, iron, maybe sodium and potassium. They're all gone, and what you end up with is silicon, aluminum silicate, aluminum oxide silicate. And they grow, you can see by their length, they grow lengthwise. They do not grow wider as time goes on. And that, I think, is because there's no alteration out here. This thing is a barrier. How much time do I have? 2? 3 minutes. Okay, so this is how the glass is altered. You've got protons on the outside. They are moving across the boundary. They are replacing cations on the inside. You have a proton flux into the rock. And so what we've said is that, okay, here's a drawing of that fracture, the water in here. Here's the glass, here's the rock, and here's a cell. We just hypothetically put a cell on the surface of the fracture. And it's the protons that are moving into this tunnel now, they move to the end they go into the rock. They replace sodium, potassium, magnesium, calcium. So that you have a flux of protons from this pH 7 water out into the rock. And if you look at the normal rate at which a rock will dissolve in seawater at pH 7.5 and 50 to 60 degrees, which is what the temperature is of that aquifer, you can, and these measurements have been made by other people, Olkers and Gislason in Iceland, you can determine that for the area of the end of this tunnel, you're moving 10,000 protons a second into that rock, and you're getting equivalent charge out of that rock back through here. This cell then is in the position to harvest the energy of 10,000 protons a second. It's a significant amount of energy. So the cell makes this barrier here on the surface. The protons enter the glass. The tunnel is initiated, and probably wasn't a tunnel to begin with, just a little indentation here. pH in the tunnel rises to 9.8. They form the clay that you saw in that picture. And the potential across here, due to the 7.5 to 9.8 pH difference, is minus 128 millivolts. That's a big charge. And it's very similar to what is produced in cells when they make their own proton gradient with those three little molecules I was pointing out early on. And the power to the cell is 3 times 10 to the minus 16 joules per second per cell because of this proton flux. The minimum energy needed for a cell is probably somewhere around 10 to the minus 20 joules per second. So you've got several orders of magnitude more energy from this process than the minimum. So the main points, the tunnels in the basalt, they must grow longer and they don't get wider. They're a channel for protons, so they diffuse from water down the tunnel out into the glass, and a cell at the entrance would be able to generate ATP from that flux. So what are the implications? These water to basalt proton gradients had to be available on Earth from the time the Earth formed, when there was solid rock on the surface and water. This could have been going on since the beginning of the planet. There have been tunnels very similar to the ones I showed you in 3.5 billion-year-old basalts on Earth. So if those are equivalent, there's evidence for life at 3.5 billion based on the same mechanism. There's also one type of Martian meteorite that has some tunnels very similar. I don't know where to go with that. Based on recent discoveries of exoplanets with rock and that have rock and water, maybe 25% of the planets near us could use this mechanism to generate energy to drive metabolism. That's it.
We have time for one quick question.
I love the idea, but I don't understand why you would only have one cell sitting there and you would just get one long tunnel. Why wouldn't you imagine a cell next to it, next to that, and next to that, and just eroding the whole surface away?
So the question was, why is there just one cell and doesn't the whole surface? I didn't explain everything. I think that's a really good point, but I think the cell must control its local environment by laying down a proton impermeable layer around it, so that the protons have to go through the cell. Because if they didn't do that, they would just totally erode the surface, and you would have no tunnels. So I think there must be another component, which was actually drawn in the model, but I didn't have time to talk about it. There's a poster tonight, 7 o'clock, if you want to see more, or throw some tomatoes.
So we actually have time for one more question. Yes?
I'll repeat it.
something wrong with how you're thinking about energy?
That could be, and I'd like to talk to you about it. So the question is, am I thinking about energy in the wrong way? So I'm thinking about the potential across the boundary of a cell, which
Well, your mineral membrane, at least in your diagram, was about 500 angstroms. And the membrane on a cell is about 30 angstroms. So when you talk about a potential difference, the distance is over which it operates is important parameters. So it's really, these mineral membranes you showed are just gigantic.
so the membrane, there was a tunnel, the clay inside and the glass outside. Is that what you're talking about?
On your diagram, yeah.
Oh, not the diagram, not the. All right, well, I think we'll have to talk. So.
Yeah, well, yeah, please discuss later. Thank you very much.